Welcome to Cosmic Sedation, where we drift through the cosmos for a peaceful night's rest. Tonight, we explore the oldest star in the universe is still alive, shining brightly through billions of years. If you enjoy these journeys, hit that subscribe and like button. It means a lot. Drop a comment letting us know where you are tonight and what time you usually fall asleep. As the stars begin their slow dance above, let's embark on this tranquil voyage together. HD 140,283, a star older than life itself, continues to fuse hydrogen into helium in its core. This ancient process has outlived every species that has ever walked the Earth. At its heart, temperatures exceed 13 million degrees Celsius, where hydrogen atoms are crushed together with such force that they merge to form helium. Despite being one of the oldest stars known, HD 140,283 is still in its main sequence phase, a testament to how long it takes for even the simplest nuclear reactions to exhaust their fuel. The core of this ancient star operates on an accelerated timescale due to intense gravitational forces. For every second that passes on Earth, millions of seconds pass within its dense heart. This relentless fusion cycle has been ongoing for 14.5 billion years, older than our universe as we understand it, according to some measurements. Yet, this core still hums with the same energy that has sustained it since before stars like our Sun even existed. The star's diameter is about 1.6 times that of our Sun, reflecting its lower mass and cooler temperature. HD 140,283's surface temperature is approximately 6,000 Kelvin, making it cooler than many younger stars. This cooler environment allows for a slower rate of hydrogen fusion, extending its lifetime to another billion years or more before it begins its slow transition into a white dwarf. The star's relatively small mass of 0.8 solar masses contributes to this longevity. Less gravity means a gentler compression of gas in the core and thus a slower consumption of fuel. This balance ensures that HD 140,283 continues to shine with an unyielding consistency. Beyond its photosphere, where light escapes into space, temperatures drop dramatically. Here, heat transfer occurs primarily through radiation rather than conduction or convection, as there are no molecules to carry pressure waves in this near-vacuum environment. This vast emptiness contrasts with the intense activity at the star's core, where every second sees approximately 600 million metric tons of hydrogen converted into helium. To put this in perspective, if Earth were a similar fusion reactor, it would convert all its mass into energy in less than 2 years. The star's composition reveals secrets about the early universe. With fewer heavy elements compared to younger stars, HD 140,283 contains materials formed from the very first generations of stellar explosions. The iron in our blood was likely forged in such ancient supernovae, long before this star began its life. This connection between a human body and one of the oldest objects in the universe is a reminder of how deeply we are intertwined with cosmic history. Every breath you take carries within it particles that have been part of stellar evolution for nearly half of time's known existence. As HD 140,283 burns through its hydrogen, it subtly changes the surrounding interstellar medium. Its ultraviolet radiation ionizes nearby gas clouds, influencing star formation in distant regions of space. This ancient star, while stable and unchanging on human timescales, plays an ongoing role in shaping the galaxy's future. HD 140,283, an ancient star located just 190 light-years away in our cosmic backyard, defies the conventional understanding of time itself. This star is older than the universe. According to some measurements, it predates even the Big Bang by a few million years. For context, if we compress the entire history of human civilization into a single day, HD 140,283 would have already lived through nearly 400 such days. Its surface temperature hovers at around 6,000 Kelvin, familiar yet distant compared to its more energetic peers in the cosmos. The core of this ancient star reaches temperatures exceeding 15 million Kelvin, hotter than any place on Earth could possibly be. This stellar furnace remains stable and continues to fuse hydrogen into helium, a process that has outlived every species that has ever walked the Earth. HD 140,283's mass is approximately 80% that of our Sun, a modest scale for such an ancient luminary. Its diameter spans about 1.6 times wider than Earth's own life-giving luminary, yet its cooler temperature allows it to burn hydrogen at a slower rate, contributing to its remarkable longevity. The star formed from a cloud of gas containing minimal amounts of heavy elements, marking its origins as part of the very early universe when such materials were scarce. This makes HD 140,283 one of the earliest stars in the Milky Way, bearing witness to epochs where life on Earth barely resembled anything we would recognize today. The star's cooler temperature and smaller mass ensure that it will continue to burn steadily for another billion years before transitioning into a white dwarf, a dense core surrounded by an expanding shell of gas. Despite its age, HD 140,283 shows signs of activity consistent with stars far younger. It emits light across various wavelengths, indicating ongoing nuclear fusion processes deep within its core. This star's stability is due to the slow and steady rate at which it fuses hydrogen into helium, a process that will keep it shining for eons more. In contrast, human civilization, as we know it, has existed for less than 10,000 years, an infinitesimal fraction of HD 140,283's lifespan. If we were to consider each year in the star's life as a single second, then all of recorded human history would fit into just one fleeting moment. The iron in your blood was forged in stars that died before our sun even existed, a cosmic connection linking every human being back to the very beginnings of time. HD 140,283 is no exception. It contains less heavy elements than younger stars, a testament to its ancient origins and the scarcity of such materials when it formed. This star's formation occurred during an era when the universe was still rich with hydrogen and helium, but sparse in heavier elements. The fusion process inside HD 140,283 is slow yet steady, burning hydrogen at a rate far slower than larger stars do. Despite this leisurely pace, the star continues to perform its cosmic duties tirelessly. The contrast between HD 140,283's stability and human existence is stark. While HD 140,283 will remain bright for another billion years, an average human lifetime is measured in mere decades. In the vast expanse of time, our lives are fleeting blinks compared to this ancient star's enduring presence. Beyond its current state as a main sequence star, HD 140,283's future is marked by gradual changes leading up to its transition into a white dwarf, a dense core surrounded by an expanding shell of gas. This transformation will take millions of years to complete, underscoring the vast difference in time scales between cosmic phenomena and human lifespans. In another billion years, HD 140,283's hydrogen reserves will be nearly depleted, marking its shift from a main sequence star into a red giant, a phase where it will expand dramatically before shedding its outer layers. This transition is part of the natural life cycle of stars like ours and reflects the unending cycle of cosmic change that has been happening long before humans ever existed. The coldest place in the known universe is not out in deep space, but in a laboratory on Earth. Yet HD 140,283 burns at temperatures hotter than any point on our planet could possibly be. The journey to HD 140,283 begins with a gradual descent into the vastness of space. This ancient star is located in the constellation Libra, but its true significance lies not in its location, but in the profound time it has witnessed. At approximately 190 light-years away, every photon reaching Earth from this stellar giant took nearly 2 centuries to complete its journey. As you approach HD 140,283, you might expect a blazing inferno of heat and light. Yet, surprisingly, the warmth is almost imperceptible due to the sheer distance between us and it. The surface temperature of HD 140,283 hovers around 6,000 Kelvin, similar to our Sun's, but the vast emptiness of space acts as an insulating void, reducing any thermal sensation felt by a hypothetical observer on Earth to nearly nothing. This paradoxical coldness in proximity to such an ancient and enduring light source underscores how profoundly different our experience of space is from that of stars themselves. Despite its cooler surface temperature compared to other older stars, HD 140,283 maintains a stable fusion process at its core. It continues to convert hydrogen into helium, a task it has been performing for over 13.5 billion years, long before our Sun even formed. This longevity is remarkable when you consider that the universe itself is estimated to be around 13.8 billion years old, making HD 140,283 older than the cosmic timeline as we understand it. Its continued existence challenges our understanding of time and stability in the cosmos. The star's photosphere, where light escapes into space, is remarkably serene despite its age. At a diameter about 1.6 times that of our Sun, HD 140,283 presents itself as a giant among ancient stars. The surface, however, does not reveal any signs of imminent collapse or significant change. It remains in a state of quiet equilibrium. This stability is a result of its lower mass, which slows the fusion process and extends the star's life expectancy by billions more years. In human terms, this longevity can be likened to watching an ant move across a field over millennia. The absence of heavy elements in HD 140,283 speaks volumes about the early universe. The iron that fills our veins was forged in stars younger and hotter than HD 140,283. This star, formed during an era when heavier elements were scarce, contains only traces of such metals, a testament to its age. Its composition is simpler, yet it has persisted through epochs where galaxies coalesced and life evolved on Earth. The iron in your blood was created in more energetic stars that have since died out, leaving behind remnants like neutron stars and black holes. As you reflect upon this ancient star, consider the scale of its journey. HD 140,283 will eventually become a white dwarf, cooling over eons as it sheds its outer layers. The process of its death is slow and inevitable, yet each moment of its existence contributes to our understanding of cosmic time. Its light, reaching Earth after decades of travel, continues to illuminate our quest for knowledge about the universe's origins and evolution. This star is not just a relic. It is an enduring witness to the birth and growth of everything we know in the cosmos. From its vantage point in the constellation of Libra, HD 140,283 emits a constant stream of subatomic particles that carry information from the universe's infancy. These particles are far smaller than the width of an atom and travel at nearly the speed of light, yet they offer insights older than time itself as we understand it. While invisible to our naked eye, these streams are captured by Earth-based detectors that measure their arrival with exquisite precision. The particle flux from HD 140,283 provides a direct link between humanity's curiosity and the birth pangs of the cosmos. Each subatomic particle is a messenger from an era when the universe was just 13.8 billion years old, older than any other star we can observe today. These particles are predominantly protons and electrons, remnants of ancient fusion processes within the star's core. The journey these particles undertake is staggeringly long. They travel through interstellar space, sometimes for centuries before reaching our detectors. This travel time serves as a reminder that what we measure now happened in a distant past, a concept both humbling and awe-inspiring. These particles, though infinitesimally small, are the physical manifestation of events that shaped the universe's early history. The surface temperature of HD 140,283 is approximately 6,000 Kelvin, cooler than many other stars its age, yet it continues to fuse hydrogen into helium at a measured pace. This process generates an ongoing flow of particles, including neutrinos and solar wind components, that are too energetic for us to see directly, but can be detected by instruments sensitive enough to capture particles with energies exceeding 10^9 electron volts. The rate at which these particles stream from HD 140,283 is a testament not only to its longevity, but also to the efficiency of fusion processes in such ancient stars. This star, despite its advanced age, remains an active participant in the universe's ongoing evolution. The detection of subatomic streams from this distant star reveals something paradoxical about our understanding of time and space. The particles that reach Earth today left HD 140,283 hundreds or even thousands of years ago, yet they provide real-time information about what the star is doing now. This temporal disconnect creates a fascinating loop. We observe ancient events as if they are happening in the present. In this way, the universe itself becomes a vast repository of time, and these particles serve as pages that have traveled across cosmic distances to inform us of the past. The composition of HD 140,283 is particularly noteworthy for its relative paucity of heavy elements, known as metals in astronomical terms. The star formed during an era when such materials were scarce, meaning it lacks many of the complex atoms found in younger stars like our Sun. This simplicity makes each subatomic particle from HD 140,283 a unique chemical signature, offering insights into conditions that existed shortly after the Big Bang. By analyzing these particles, scientists can reconstruct the early universe's elemental abundance and understand how it evolved over billions of years. Despite its age, HD 140,283 will continue to burn hydrogen in its core for another billion years or so before transitioning into a white dwarf. The subatomic streams from this star provide us with an ongoing narrative of its life cycle, one that spans the entire history of our universe. These particles are not just fleeting visitors, but messengers that bridge vast gulfs of space and time, connecting us to a cosmic heritage far older than any human civilization could ever imagine. HD 140,283, one of the oldest stars in the universe, quietly fuses hydrogen into helium within its core. The star's surface temperature is approximately 6,000 Kelvin, a warmth that belies its advanced age and ancient origins. This process, repeated over billions of years, has shaped the very elements that make up our world. At a distance of 190 light-years from Earth, HD 140,283 is part of our local cosmic neighborhood in the constellation Libra. Despite being older than the universe itself according to some measurements, estimated at around 14.5 billion years, it remains active, continuing its slow burn through hydrogen fuel. The star's mass is approximately 8/10 that of our Sun, a size and composition that reflect its formation during an era when heavier elements were scarce. The fusion reactions occurring in HD 140,283 are not merely about sustaining the star's life. They also contribute to the distribution of heavy elements throughout space. These reactions are fundamental to stellar evolution and the eventual creation of planets like Earth. The iron in your blood, for instance, was forged in stars much like this one, long before our solar system formed. While HD 140,283 is relatively cool compared to other stars of its age, its core temperature exceeds 13 million Kelvin. It still performs a critical role. This star acts as a witness and participant in the universe's grand elemental cycle, a cycle that has been ongoing since shortly after the Big Bang. Its longevity ensures that it continues this process for at least another billion years, enriching interstellar space with elements vital for planetary formation. The iron content within HD 140,283 is notably low, containing less than 1,000th of the Sun's iron abundance. This scarcity reflects a time in the universe's history when stellar nucleosynthesis had not yet created significant quantities of these elements. Yet, paradoxically, this very deficiency allows us to study how stars like HD 140,283 contributed to the enrichment of subsequent generations of stars with heavier elements. The star's photosphere emits a constant stream of radiation into space, carrying with it information about its age and composition. This radiation travels through the vacuum of space at nearly the speed of light, eventually reaching our telescopes on Earth. Each photon carries a story from a time when galaxies were young and the universe was still in its infancy. As HD 140,283 continues to burn hydrogen into helium, it subtly influences the elemental makeup of interstellar space. This process has been ongoing for nearly 14.5 billion years and will continue until the star exhausts its fuel, at which point it will expand into a red giant before cooling down as a white dwarf. Each fusion event contributes to the creation of heavy elements that are essential for planetary formation. In this environment, sound cannot propagate because there are no molecules to carry pressure waves. Yet, the energy released from these reactions travels through space in the form of radiation, reaching our telescopes and providing insights into the universe's history. This connection between distant starlight and human observation underscores how intimately we are linked to the cosmos. The surface temperature of HD 140,283 is approximately 6,000 Kelvin, cooler than many younger stars of similar mass. Despite this relative coolness, the core temperatures exceed 15 million Kelvin, preventing any form of matter from remaining in a solid or liquid state. Beyond the star's photosphere, space is nearly a vacuum, so heat transfer occurs primarily through radiation rather than conduction or convection. However, an unexpected fact about HD 140,283 is that its magnetic field strength is unusually weak for such an ancient star, suggesting it may have lost much of its initial magnetic energy over time. The star's surface may seem calm, but it is a dynamic environment where energy flows outward at incredible speeds. The rate of fusion within HD 140,283 ensures that it will remain stable for many more years, continuing its role in enriching space with heavy elements. These elements are the building blocks for planets and life itself, making HD 140,283 a vital participant in the universe's ongoing story. As we observe HD 140,283 from Earth, we see not just an ancient star, but also a testament to the enduring processes that have shaped our universe. Its continued existence serves as a reminder of how stars like it have been essential for creating the elements necessary for life, a process that has been unfolding since long before the birth of our sun. In the deep cosmic silence that preceded the birth of HD 140,283, there was no light to guide the way. This prestellar era, known as the Cosmic Dark Ages, spanned approximately 100 million years after the Big Bang. During this time, the universe consisted mostly of hydrogen and helium, left over from the initial expansion and cooling of space. No stars had yet formed, nor were there any galaxies to light up the darkness. The temperature of the early universe was about 3 degrees Kelvin above absolute zero. This faint glow is what astronomers refer to as the cosmic microwave background radiation. It's a remnant of the Big Bang, providing evidence that our cosmos has been expanding and cooling ever since its inception. The absence of stars meant there were no nuclear fusion reactions to produce light or heat in significant quantities. Instead, space was filled with diffuse clouds of hydrogen and helium atoms, slowly drifting through the vast emptiness. Before HD 140,283 came into existence, the universe lacked the heavier elements that are abundant today. These elements, such as carbon, oxygen, silicon, and iron, are forged in the hearts of stars and scattered throughout space by supernova explosions. The first stars to form were colossal entities, known as population III stars, with masses over 100 times that of our sun. They burned brightly but briefly, their intense fusion reactions creating heavier elements before they collapsed into black holes or exploded. HD 140,283 represents a transition phase in the universe's history. It is one of the earliest stars to form after the population III era, containing only traces of heavy elements compared to younger stars. This scarcity indicates that it formed when the cosmos was still relatively pristine and star formation was just beginning. The star's surface temperature of approximately 6,000 Kelvin reflects its cooler state relative to more massive, hotter stars. In this prestellar environment, space was a nearly perfect vacuum, devoid of structures or features we now associate with galaxies. However, the universe was not entirely featureless. It contained tiny fluctuations in density that would later grow into the seeds of cosmic structure. These minute variations, detected through precise measurements of the cosmic microwave background radiation, provided the blueprint for future galaxy formation. Before any star ignited, there were no planets or life forms to witness the cosmos evolution. The universe was a place where time moved slowly, with vast stretches of emptiness between sparse pockets of matter. It took approximately 13.5 billion years for enough heavy elements to accumulate, allowing smaller stars like HD 140,283 to form and persist in their quiet fusion cycles. These ancient stars are cosmic chronometers, ticking away the eons since the dawn of time, when nothing existed but the potential for light and life. The birth of stars like HD 140,283 signifies the transition from a simple hydrogen-helium universe to one rich with heavier elements. As these early stars died and scattered their ashes into space, they laid the groundwork for future generations. This process took place over billions of years, gradually enriching the cosmos with the raw materials needed to form planets and eventually life itself. HD 140,283, by contrast, is a relic from this era, still fusing hydrogen in its core after nearly 14 billion years. In the vastness surrounding HD 140,283, there are no sound waves or molecular collisions to carry energy. The heat radiating from the star spreads out into space through radiation alone, gradually dissipating into the cold vacuum. This stark environment underscores how profoundly different our familiar world is compared to the conditions where stars like HD 140,283 formed. It's a reminder of the cosmic scale and the long journey it took for elements in our bodies to be created. The universe before HD 140,283 was a place of extreme simplicity, yet it contained within it the seeds of complexity. The first stars that ignited after this ancient star provided the initial burst of energy needed to form galaxies and eventually planets. They set into motion a chain of events that led not just to other stars, but also to the conditions necessary for life to arise on Earth and perhaps elsewhere. This cosmic timeline, stretching back billions of years, reveals how intricately connected we are to the ancient processes that shaped our universe. In the constellation of Libra, a star known as HD 140,283 continues to glow steadily despite being older than many theoretical timelines for the universe itself. At approximately 6,000 Kelvin, its surface temperature is cooler than expected for such an ancient entity. This paradox becomes clearer when we consider that this star has been burning for over 13.5 billion years, longer than the age of the cosmos, as some models suggest. The core of HD 140,283 fuses hydrogen into helium, a process that has sustained it for billions of years and will continue to do so for another billion. This longevity is not just remarkable, but defies our understanding of stellar evolution. Stars typically expand and cool as they age, yet this ancient star remains in its main sequence phase, maintaining a steady fusion rate despite the passage of time. Its stability contrasts sharply with the volatile life cycles of younger stars, which quickly enter their red giant or supergiant phases. HD 140,283's composition is sparse in heavy elements, indicating it formed during an era when these materials were scarce. This lack of complexity paradoxically helps explain its endurance. Fewer heavy elements mean less mass to fuel rapid expansion and collapse. The star's relatively low mass, about 8/10 that of our Sun, contributes to its longevity. In contrast, more massive stars burn through their fuel much faster, often ending their lives in spectacular supernovae within just millions rather than billions of years. At a distance of 190 light-years from Earth, HD 140,283 is considered quite close on cosmic scales. This proximity allows us to study it with remarkable precision, revealing details that challenge our understanding of stellar aging. Despite its age, the star remains in equilibrium, balancing outward pressure against gravity with a core temperature exceeding 15 million Kelvin. This internal heat is necessary to sustain fusion, but also ensures stability over time. The paradox here lies not just in its age, but in the fact it shows no signs of imminent collapse or expansion. Comparing HD 140,283 to human life offers further perspective on its endurance. While humans live for mere decades, this star has witnessed countless epochs and cosmic events since its formation. It was already a mature entity when Earth formed 4 billion years ago, yet it shows no signs of decline or exhaustion. This ancient star continues to burn with the same vigor as when it first lit up the nascent universe, challenging our perceptions of time and stability. Reflecting on HD 140,283's future, we see another layer of paradox in its longevity. In a billion years, it will likely transition into a white dwarf, ceasing nuclear fusion, but remaining visible for billions more as it gradually cools. This phase is far longer than the period during which it has been burning hydrogen, offering a glimpse into an enduring existence that spans multiple stages of stellar evolution. The star's current stability and future transformation underscore its unique position in cosmic history. One might wonder how such a star could have formed so early in the universe's timeline. HD 140,283 likely coalesced from primordial gas clouds, containing few heavy elements that would have seeded later generations of stars. This scarcity of heavier materials allowed it to form earlier and persist longer than many other stellar bodies. Its formation period predates even the earliest galaxies, making it a relic of an era when the universe was in its infancy. Despite being one of the oldest known stars, HD 140,283 remains active, fusing hydrogen into helium at a rate that keeps it stable for now. The star's diameter is about 1.6 times that of our Sun, reflecting its lower mass and cooler temperature. This size contributes to its longevity by reducing the gravitational pressure needed to sustain fusion reactions in its core. Despite its relatively small size compared to other stars in the Milky Way, HD 140,283 plays a crucial role in the cosmic ballet that governs stellar motion. Its gravitational field extends far beyond its visible light, subtly influencing the orbits of nearby celestial objects over vast distances. This interaction is akin to how a large tree might sway branches of smaller trees nearby. The star's mass, about 0.8 times that of our Sun, creates ripples in space-time that guide the paths of neighboring stars and planets. HD 140,283 exists within a complex network of gravitational forces that include dense molecular clouds and other stars. These interactions are not uniform. Some celestial bodies experience more pronounced effects than others. For instance, if a star passes near a region rich in gas and dust, it could be affected by the additional mass concentrated there, altering its path significantly over time. This delicate dance of gravitational attraction shapes the architecture of our galaxy. The core temperature of HD 140,283 reaches an astounding 15 million degrees Celsius, far hotter than any point on Earth. This extreme heat is necessary for hydrogen fusion to occur, which sustains the star's ongoing life cycle despite its advanced age. Yet paradoxically, the cooler surface temperature of 6,000 Kelvin suggests that HD 140,283 has been in decline for some time, maintaining a delicate balance between youth and senility. This ancient star continues to fuse hydrogen into helium, ensuring it remains active. The ancient star's position within the Milky Way is influenced by the galaxy's dynamic evolution, its spiral arms and central bulge exerting a pull on stars like HD 140,283. Over billions of years, these interactions have shaped the paths of countless stars and planets in its vicinity. The gravitational forces at play are so subtle that they can only be detected with precise measurements, yet their cumulative effect is profound. HD 140,283's gravitational influence extends beyond just altering orbits. It also plays a role in the formation and evolution of nearby stars and planets. The gentle nudges from this ancient star contribute to the intricate dance that defines our galaxy's structure. Over time, these interactions can lead to significant changes in stellar systems, illustrating how even seemingly insignificant cosmic players leave their mark on the universe. The surface temperature of HD 140,283 is approximately 6,000 Kelvin, which might seem cool for a star of its age. However, this cooler temperature indicates that it formed during an early period when heavy elements were scarce. Its composition reflects conditions in the very infancy of our universe, offering a glimpse into the primordial cosmos. This ancient relic continues to burn hydrogen, maintaining stability for another billion years before becoming a white dwarf. HD 140,283's journey through space is not only influenced by its immediate neighbors, but also by distant supermassive black holes and other massive objects scattered throughout the galaxy. These far-reaching forces create a cosmic tug-of-war that subtly alters the star's trajectory over eons. The gravitational pull from these distant entities can cause HD 140,283 to oscillate in its orbit, creating slight deviations that accumulate over time. This phenomenon is similar to how ocean tides are influenced by both the moon and the sun, even though their effects are fainter. Despite being one of the oldest stars, HD 140,283 remains a vital participant in galactic dynamics. Its interactions with other celestial bodies highlight the interconnectedness of our universe. The star's small size belies its significant impact on nearby systems, demonstrating that even relatively minor players can shape cosmic events. This delicate balance between influence and insignificance underscores the intricate nature of stellar evolution within the Milky Way. The gravitational field of HD 140,283 extends far beyond its visible light, affecting not just stars, but also clouds of gas and dust in its vicinity. These interactions play a crucial role in the formation of new stars and planetary systems. The gentle pressure exerted by the star's gravity can compress nearby molecular clouds, initiating the process of starbirth. This cycle of influence and creation underscores how HD 140,283 contributes to the ongoing story of our galaxy. As HD 140,283 continues its journey through space, it serves as a reminder of the delicate balance that governs stellar motion. The gravitational forces acting upon it are not static, but dynamic, constantly shifting and adapting over time. This ever-changing environment ensures that even ancient stars like HD 140,283 remain integral to the cosmic dance. The star's influence is particularly pronounced in its immediate neighborhood, where it helps sculpt the... In the earliest moments of our universe, there was no light. For nearly 13.8 billion years after the Big Bang, the cosmos remained a pitch-black expanse, devoid of stars or galaxies to illuminate it. This period, known as the Cosmic Dark Ages, was characterized by an eerie vacuum of radiation and matter. Yet within this void, something profound occurred. A series of quantum fluctuations seeded the future stars with the first particles. During these starless epochs, the universe expanded rapidly, cooling from its initial fiery state into a vast, empty space. This expansion allowed hydrogen to spread evenly throughout the cosmos, creating ideal conditions for the eventual formation of stars. The cosmic microwave background radiation, which we observe today as faint echoes of the Big Bang, began to form during this period, marking the transition from darkness to light. During these epochs, the universe was a near-perfect vacuum, with matter distributed so thinly that it took eons for gravity to pull together enough gas into dense clouds capable of igniting nuclear fusion. HD 140,283's composition tells an ancient tale of scarcity. With fewer heavy elements than younger stars, it bears witness to a time when nuclear fusion was simpler and less complex. The iron within its core was not forged here, but born from earlier cosmic collisions that enriched the interstellar medium with heavier elements. This star's existence is a paradox. Though it formed in an age where matter was sparse, its presence now underscores the abundance of heavy elements created by prior stellar generations. Despite being older than the universe according to some measurements, HD 140,283 contains less iron and other heavy metals than stars born just a billion years later. The first stars, known as population III stars, emerged as these hydrogen clouds coalesced under gravity's pull. These behemoths were massive and short-lived compared to their modern counterparts. They burned through their fuel at an accelerated rate, leaving behind iron cores that would eventually collapse into black holes or supernovae. HD 140,283 stands in stark contrast, having formed during a period when the universe was less enriched with heavy elements. It is one of the few surviving remnants from this era, providing a rare glimpse into an age when the cosmos was still young and uncharted. While HD 140,283 continues to fuse hydrogen into helium, its core temperature remains a staggering 15 million Kelvin, a furnace capable of fusing lighter elements but not creating heavier ones. This process has kept it stable for billions of years and will continue to do so for another billion more. Despite being older than the universe according to some measurements, this star's fusion rate is remarkably constant, like a ticking clock that defies our understanding of time. It radiates energy at an approximate temperature of 6,000 Kelvin, cooler than many stars of similar age. At its surface, HD 140,283 glows with an approximate temperature of 6,000 Kelvin, cooler than many stars of similar age. This relatively low temperature indicates a lower mass and slower burn rate compared to larger, hotter stars. Yet this coolness belies the immense pressures and temperatures within its core. It is a living testament to the universe's first light, carrying forward a legacy that spans nearly half the time since the Big Bang. HD 140,283's stability is a remarkable example of how some ancient stars can persist for such long periods, continuing their fusion processes with an unwavering consistency. The star's diameter is about 1.6 times the size of our Sun, reflecting its lower mass and cooler temperature. This difference in size and luminosity provides insight into the varied life cycles of stars across cosmic history. As HD 140,283 radiates its energy outwards into the void of space, a boundary emerges where its influence diminishes to an imperceptible point. At approximately 185 million kilometers from the star's surface, roughly equivalent to 2 astronomical units, the photons emitted by HD 140,283 become less frequent. This distance marks a subtle transition zone where the star's gravitational pull still resonates, but its light begins to spread thinly across the vast emptiness of interstellar space. At this boundary, hydrogen atoms are ionized by HD 140,283's intense ultraviolet radiation, creating a faint glow known as the Sturmgren sphere. This region marks the outermost extent of the star's visible influence, where light and matter interact in ways that shape our understanding of stellar evolution. Yet, paradoxically, this cooling effect does not extend indefinitely into the void. In fact, deep within our galaxy's heart, some regions reach temperatures as low as 27 Kelvin, colder even than the outskirts of HD 140,283's influence. This contrast between localized stellar warmth and galactic cold spots underscores the complexity of cosmic thermodynamics. At this boundary, the temperature drops to approximately 3,000 Kelvin, significantly cooler than the star's surface at 6,000 Kelvin. Yet, beyond this point, space becomes nearly a perfect vacuum, with hydrogen atoms so sparse that it would take more than 1,000,000 cubic light-years to contain one atom. This emptiness stretches for trillions of kilometers in all directions, punctuated only by distant galaxies and occasional wandering interstellar clouds. The sheer scale of this emptiness dwarfs even our most grandiose concepts of space, challenging human comprehension. At the edge of HD 140,283's influence, the density of matter is so low that a single photon may travel for trillions of kilometers before encountering another particle. This region is devoid of significant gravitational influences, making it an ideal laboratory for studying fundamental physics in near-perfect isolation. Here, cosmic rays and distant galaxy light provide the only signs of activity, offering astronomers unique insights into the universe's most basic properties. With a current age of approximately 13 billion years, HD 140,283 is one of the oldest stars known to us. Its fusion process, converting hydrogen into helium at an estimated rate of 0.1 solar masses per year, ensures it will continue shining for another billion years or so. This longevity is remarkable when compared with the fleeting existence of human civilizations, which have not even reached their millionth year. Yet this star's endurance is but a fraction of the cosmic timeline. Its life cycle is brief in comparison to the universe's vast expanse. As we observe this boundary where influence fades into void, it serves as a poignant reminder of our place within the cosmos. Within this boundary, the photons from HD 140,283 travel at an unfathomable speed of 299,000 kilometers per second. These particles have traversed a journey that began millions of years ago, yet they reach us with a consistency that belies their age. Each photon carries not just light, but also the essence of time, tracing back to an era when the universe was younger, simpler, and less populated by stars like ours. This boundary is more than just a point in space. It is a bridge between epochs, connecting past, present, and future. HD 140,283, an ancient star located just 190 light-years away in the constellation of Libra, exemplifies cosmic endurance and resilience. This star, estimated at about 14.5 billion years old, defies conventional timelines, existing even before our universe, as we know it was thought to have begun. As it burns hydrogen into helium, HD 140,283 remains a beacon from the earliest epochs of stellar formation. As hydrogen in its core gradually depletes, HD 140,283 will transition into a red giant phase, swelling to sizes far greater than its current diameter of about 1.6 times that of our Sun. During this expansive period, the star's outer layers may expand and cool, casting a dim glow across the nearby interstellar space. This stage represents the final act before it begins its irreversible path toward becoming a white dwarf. The transformation into a white dwarf signals the end of HD 140,283's active life cycle. In this state, gravity will compress the star to an incredibly dense core, where electrons resist further collapse due to their quantum mechanical properties. The mass of the resulting white dwarf will be comparable to that of Earth, yet it will pack this within a volume about as large as our planet. Despite its advanced age and relatively modest size, HD 140,283's continued fusion underscores its remarkable longevity compared to human lifespans or even the existence of complex life. This endurance prompts us to consider how fleeting our presence is in the broader context of cosmic time. The star's resilience stands as a stark reminder of the vastness and complexity of the universe. As we observe HD 140,283, it serves as a bridge between epochs, linking the earliest moments after the Big Bang with the present day. It continues to fuse hydrogen into helium in its core, a process that has outlived all known species on Earth. This ongoing fusion is not just a testament to its age, but also an integral part of how stars contribute to the cycle of cosmic evolution. During this phase, HD 140,283 will shed its outer layers into space, creating a beautiful planetary nebula that will illuminate nearby regions for millennia before fading away. The core left behind will be a white dwarf, but there's an intriguing possibility. If HD 140,283 was significantly more massive than it is now, it could have collapsed further into a neutron star instead. However, given its current mass of approximately 0.6 solar masses, the star lacks the necessary gravitational force to overcome electron degeneracy pressure and form such an extreme object. Instead, it will cool over billions of years, eventually becoming a cold, dark stellar remnant floating in interstellar space. As HD 140,283 cools and fades, it leaves behind a trail of heavy elements that were once part of its core. These elements will eventually find their way into other stars, planets, or even future solar systems. This cycle underscores the interconnectedness of all cosmic objects, from the smallest subatomic particles to entire galaxies. In this way, HD 140,283's legacy will live on, woven into the fabric of future celestial bodies that are yet to be born. Despite its advanced age and relatively modest size, HD 140,283 continues to burn hydrogen in its core, a process that has outlived all known species on Earth. This ongoing fusion is not just a testament to its age, but also an integral part of how stars contribute to the cycle of cosmic evolution. By synthesizing elements through nuclear reactions at temperatures exceeding 15 million degrees Celsius and pressures equivalent to millions of atmospheres. HD 140,283, an ancient flame flickering in the cosmic night, continues its silent dance of fusion, older than any life we know. As this journey through space comes to a gentle close, rest assured you've been part of something vast and serene. Thank you for joining us tonight on Cosmic Sedation. If you enjoyed the ride, feel free to subscribe and leave a like. Good night, and may peace guide your dreams as it has guided the stars.